This problem states if f is a one-to-one function with domain x and range y, prove that f inverse is a one-to-one function with domain y and range x. So, with a proof problem like this, what strategies of proof can you think of that you know? Is this a good problem to try to prove directly? What I've drawn here is a diagram that shows x and y and the function f, which is a one-to-one function, and this is a predicate logic statement, which is a very formal way of saying for all values in the domain, for any x, there is a value y in the range y such that for all z in x, so if I could draw a z here, or maybe z is x, another name for x, that for any value z in x, if f of x is maps to y, and if z also maps to y, then z has to be equal to x. That's if it's a one-to-one function. You can't have more than one different ones mapping to the same value in a one-to-one function. This long logic statement is saying for any value in here, there is one that it maps to, and for all values in the domain, if it also maps to y, then it has to be the same element as the one that maps to y. That's one way of trying to put it. So this statement right here is just a formal way of saying f of x is a one-to-one function with domain x and range y. So if we start with this, what can we do, assuming that f inverse is the function that maps y to x? So we have to figure out how to prove that f inverse is a one-to-one. What do we need to use? We could use this. This is something, a theorem that says the function of the inverse of that function always equals the original value. This is saying if f is a function that maps from x to y, then if you take the inverse, it gets you back to x. Is this useful? Yes, as I've thought about it, if you define an inverse function as a function which, when applied to a given function with a value x, if you take f inverse of f of x, it equals the original x. See how if you go from here to here with f, and then you go back to the same one with f inverse. Then the domain of the function f is x, and its range is y. Now, if you take the inverse of the original function, you get back the original value. Then the input to the inverse has to be the range of f of x, which is y. And what it returns is a value in the range of the original x, which is in x. Yeah, so the domain of f inverse is y, and the range of f inverse is x. I'm sure there's a much better way of proving it. If you have one, be glad to see it in the comments. In this problem, I worked out my solution in advance. If you have another solution, that would be great to hear about in the comments. The question is, if f has an inverse function, f minus 1, that's the inverse notation, prove that f inverse has an inverse function and that the inverse of f inverse is f. And so the main strategy I tried to use was called a proof by contradiction, where I assume that the thing that I want to prove is false, and then I show how that seems to lead to a contradiction. First of all, this step number 1 in orange is what is given. We're saying, okay, f has an inverse function, and that inverse function is f to the f minus 1, f inverse. By the definition of an inverse function, we're saying f inverse of f of x is equal to the original x, which is saying if we're going from x to y with the function f, we're saying that if f has an inverse function, so the inverse function is the one that leads y back to x, which is what we're saying here. We're saying the inverse function of f of x is x. Now suppose f inverse is not equal to f, but some other function g, which is not equal to f. So we're saying that the inverse of this function, which goes back to y, is not f, it's something else. So we're saying that the f inverse function is the one that goes this way. So the f inverse of y is equal to x. And now to get back to y, we take some other function, g, supposing that g is some other function that takes you back from x to y, given that f of inverse of y is x. Then g of f inverse of y is equal to y, because g is the inverse of f inverse, and it takes you back to the original value. But still, we still have f of x equals y. And now we're saying that g of f inverse is equal to y also, but g and f are not the same function. Kind of the definition of a same function is that give for every possible value, they give you the same output value. If two functions for the same input give you the same output, then they're the same function. So that's a contradiction to say that G is the inverse of F inverse, but it's not equal to F. So that's a contradiction to say that the inverse of F inverse is not equal to F, given that the inverse of F is F inverse. And so since we ran into a contradiction by asserting that F inverse inverse is not equal to F, then that assertion must be false, and F inverse inverse must be equal to F. This problem says find the inverse of f of x equals the square root of 1 minus 4x squared, where the domain is from 0 to 1/2 on the closed interval. So let's write this down first. The domain is 0 to 1/2. And quickly, by looking at this function, let's see if we can figure out the range. If x is 0, then this is the square root of 1, which is 1. Now, if x is 1/2, 1/2 squared is 1/4. 1/4 times 4 is 1. 1 minus 1 is 0. The square root of 0 is 0. So the range is from 0 to 1. We'll want to know that later when we're checking the eventual answer that we get. Now, the technique for finding the inverse of a function, the form of the inverse, if we say that y is the output of this function, and we want to find out what function on y gives you x. Have you learned this before? If you interchange x and y, this is the technique that I was taught. If we say that x equals, and we start with the same exact function, but swapping with x and y, 1 minus 4y squared, and we perform the operations to get this back to being a function of y. First of all, we can square both sides. Now, next is, if 1 minus this is this, then 1 minus this is 4y squared. So we can move the 4y squared and we can subtract both sides by x squared. So we get okay. What next? We divide by 4. And now, since it's y squared, we just want to take the square root. So this is the result of the inverse. And if we want to check this answer, if we want to say if this is the inverse of x, then it should be that the original function only operating instead on x on should return x. Okay, let's do this. Now, let's plug in this. 1 minus a square root 1 minus x squared over 4. This is the square root of this squared, just returns the inner 1 minus x squared over 4. Okay, the 4 and the 4 cancel out. 1 minus 1 minus minus plus x squared. 1 minus 1 is 0, plus x squared is x squared. Square root of x squared is x. Now, what is the domain that we accept? It's the range of the original function. So if we say this, specifically we're limiting this to this domain. Now, if we consider between 0 and 1, if x is 0, then 1/4, the square root of 1/4 is 1/16. Interesting. Oh, of course, I think I spoke wrong. If x is 0, 1 minus 0 is 1. 1/4. Square root of 1/4 is not 1/16, it's 1/2. And if x is 1, 1 minus 1 is 0. That makes sense. Then the range is from 0 to 1/2. Okay, that matches up, and we get back x. So, sometimes you double check, and it looks like that is the inverse of square root of 1 minus 4x squared on the domain 0 to 1/2. This problem says prove that f and g are inverses of one another, where f of x is the square root of 2x plus 1 with the domain x is greater than or equal to negative 1/2, and g of x is 1/2 x squared minus 1/2 for x is greater than or equal to 0. So what do functions need to have as far as properties go to be inverses of one another? And what do their respective domains and ranges have to have in common, or be? What property needs to be with their domains and ranges? If you know that, then you have a strategy to go forward to prove that these are inverses of one another. Let's draw a picture of the domain of f of x. This is the set of all numbers greater than or equal to negative 1/2. And we'll find out. Let's say that x is negative 1/2. 2 times negative 1/2 is negative 1. Negative 1 plus 1 is 0. And this is an increasing function. So the range is x greater than 0. We'll put D for domain, and range is okay. Now, let's say this was some particular x, just so we're not getting things confused. Let's say this is some a, and this is the function f, and this is the value f of a. This is the image of a. Okay? Now the function that is the inverse, if g is the inverse of f, if we plug in f of a, we have to go back to a, right? So the way to show this, as we've done in previous problems, is we will substitute this x with this and see if we get back the original x. So this is f of x. Now this substituting for x is all of this. Okay, let's distribute the 2 over 2 times 1/2 x squared is x squared. 2 times negative 1/2 is minus 1, plus 1. Minus 1 and plus 1 cancel out. Square root of x squared equals x. So we've shown that if we start in all x greater than negative 1/2, mapping it onto x greater than or equal to 0, if we start with something here and we go to here with f, we will get back to the original one with g. So we've proved that it works from going from here to here, going back to the same value. Notice that the domain is this. The range of the f is the same as the domain of g. We can also show that if we start with the set of all values of x greater than or equal to 0 and pick some particular value here, the one that goes from this domain is g. This is g of x. Let's see what the range of g of x is. Now this is all positive values, greater than or equal to 0. So this is, let's start with x equals 0. 0, 1/2 times 0 squared is 0. 0 minus 1/2 is negative 1/2. And as x increases, this gets bigger. So x is greater than or equal to negative 1/2. So we can see that for this domain, the range of g is the same as the domain of f. And now we want to make sure that if we go from a to g of a with the function g, if we plug in g of a into f, We'll see if we go back to A. We'll do that by doing what? What do we substitute for x right here? This right here, right? So we'll put 1/2. Now x is square root of 2x plus 1. Now x is squared minus 1/2. Okay. We're squaring this square root, which means these two cancel out. So we've got 1/2 2x plus 1 minus 1/2. Okay, let's distribute the 1/2 over the 2x plus 1. 1/2 times 2x is x. 1/2 times plus 1 is plus 1/2, and minus 1/2. The plus 1/2 and minus 1/2 cancel out, which means it's equal to x. So we've shown that we can go from f to g and back to f, and we've substituted f of x and g of x so that we can go from g of x to f and back, and we always get back x. Let me say that more clearly. We've shown that we've shown that, and we can see that the domain of f is the same as the range of g, and the domain of g is the range of f. And so that proves that f and g are inverses of each other. This problem says prove that not every polynomial has an inverse function. So how would you prove that? Think of a technique that can be useful when you're trying to prove that it is not the case that, if this is a set of all possible polynomials, let's call this set P, the set of all polynomials. How do you prove that there are some that don't have an inverse function? Think of a counterexample. Can you think of an example of a polynomial that you can prove doesn't have an inverse function? Let's say here is a domain, here's a range, let's say that f is a polynomial function. This is a, this is f of a. Can you think of a polynomial f for which there is no function g that maps f of a back to a? Remember how with inverses, it needs to be possible that the inverse of the original function of x equals x. This is a property of inverse functions. Also, we've seen that the domain of f of x equals the range of f inverse of x, and also the domain of f inverse of x equals the range of f of x. We've seen that in previous problems. Let's draw a picture of a function that probably doesn't have an inverse function. Let's say f of x equals x squared, and on the domain from negative infinity to infinity. So we're saying all values, the whole domain of x squared. Let's pick this value right here, -2. This would be -4, right? If f of x is x squared, f of 4, I didn't mean to say -4. F of -2 equals -2 squared equals 4. Is there an f inverse function so that f of 4 equals -2? Let's use the technique. We'll say f of x equals x squared equals some y, right? Now let's substitute x and y. We can do y squared equals x. Now if we want to get just y, we have to take the square root. So this is supposed to be the inverse of f of x, but on the domain that we stated, from negative infinity to infinity, this is only, the domain is only defined for positive values of x, right? So in that sense, there is no inverse to the function x squared for negative values of x. So that's one example. If you take f of x equals x squared for all values of x on its domain, there is no inverse. So we've just proved that there's not an inverse for every polynomial function. You can think of some others too and prove it by, the most important thing was not to find, well, finding a single counterexample proves that it's not every polynomial has an inverse function. The important thing from this problem was to learn how to show that a given polynomial on a given domain doesn't have an inverse.